Good evening, everyone. Good evening, all.
Good evening.
Hello, sir. Good evening, sir.
Yeah, good evening. Uh,
Yes,
I
sir.
can try to load my slide and see.
Okay. Sir, okay, sir. I'll just 2 minutes. You can wait, sir.
Yeah, no problem. Let me just try
Yeah,
if
yeah, you can
the
try,
thing
sir.
is working.
Yeah, you can just. Yes, sir. Now you can try. Yes,
Yeah,
sir.
is it coming?
Yeah, yes, sir. Yes, sir. It's coming.
Okay, good. So you can do your thing. Yeah.
Yeah, yeah. Yes, so we'll start the session. So before that, a very good evening to all the participants and welcome to the second day of AICTE ATAL FDP on future perspective of AI and data sciences, algorithms and applications. For this session, we have with us Professor Soumyendu Raha as a guest speaker. Before he starts his talk, let me take a privilege to introduce him. It's a great pleasure to have Professor Soumyendu Raha as our speaker of the next session. He is currently working as professor at Department of Computational and Data Sciences. Before he joined Indian Institute of Science, he has multiple academic and industrial experience. Like he was working as assistant professor at Computer Science Department in North Dakota State University, United States. Lecturer in Computer Science Department, University of California, Santa Barbara, US. Advisory software engineer, IBM Corporation Microelectronics Division, East Fiscal New York, US. During his tenure at IISc, he has visited many leading international universities and institutes, including Oxford University, Sokolov Institute of Research in USSR. He has been awarded Summerfield Graduate School Fellowship at University of Minnesota and Graduate School Scholarship at Minnesota Supercomputer Institute. Professor Raha has multiple research expertise and interests, including computational study of stochastic differential algebraic and stiff stochastic differential equations, and stability stochastic study of constraint dynamics. So he has published. I mean, these are not very. They are very few things I'm talking about. So he has multiple directions, including even uh, other different areas he's working, including the math, biology, etc. So he has published many of his research work in prestigious high-impact journals like SAM, Journal of Scientific Computing, Journal of Computational Physics, Bioprocess and Biosystem Engineering, Ecological Complexity, Proceeding of Royal Society, London A, Chaos, Solitons and Fractals. Journal of there are a few names what I am talking about, but he has many or other leading high-impact journal publications he has. So I'd like to invite Professor Soumyendu Raha to host the next session. And the title of his lecture is Uncertainty Modeling Computations with Stochastic Differential Equations. Sir, please take it. Sir, the audio is not, you're muted, sir. You're muted.
Thank
Yeah.
you, Chikita.
Yes.
Uh, Thanks for the kind invitation to speak. So I will today evening I will try to present a new topic, that is that we have worked on with my PhD student who graduated last year. So these are stochastic, dynamical models, but with constraints. So these are very useful in this neural network or GAN-like things that are upcoming, especially stochastic neural networks and things like that. So I will try to explain some of the mathematics and some of the computation. There are some intricate mathematical side also, which I will try to make it easier, as easy as possible for an engineering audience. Okay, so in order to preserve the bandwidth, I'm switching off my video and only keeping the audio. Okay. Okay. So you can see my slide, right, Nachiketa?
Sir, slide is appearing.
Okay, so I'm starting. Okay, thank you. Okay. So this is like a stochastic dynamics, but sometimes you need to during learning, for example, you need to learn some variables from a given data with maybe on a manifold, for example. So that is where it is useful. And so something this a lot of computer science people pursue this stochastic learning kind of study. So these models also occur naturally there. So this is a very simple model. Like it comes from this this control thing. So just think of a particle moving under gravity, and then but we want it to take a specific path. Okay, and so this kind of dynamics, like a simple thing, like you have a acceleration term, and so you have an acceleration or like a velocity term, and then you have this momentum term, and everything is subject to this this particular path. So if you want to do that, then of course there will be an extra variable like a lambda, which will be either a control input or just a parameter in case of a learning model that needs to be evaluated. So these are called technically differential algebraic equations, like some constraint, like you can think of constraint dynamical system thing, dynamics with constraint. Now this is like an example computation. So if the path is given in a parameterized, like a parametric way. So in a parameterized way, so t is a parameter and it's in the xy plane, just two-dimensional, and it is given by a potential that is gx, and we want it to take this particular path, and before the particle falls into the the attractor, and so this kind of thing is the differential algebraic equation. You can see the computed paths. Okay, so you can see this these dotted lines basically give this this systematic way of the orbits in converging into it. And else, if you do not have a control, you can go in any other way, so that is why the control is needed. Okay, so then another example is like a network. So these are half-field network, and you can think of it as like diffusion networks that people talk about nowadays in the context of neural nets and all this. So these are diffusion networks, but not static. So you can think of these are like many layers. So, and the layer is defined by your this each time step. So if you discretize this differential equation, then at every time step you can represent one of the layers of the network, and you go from layer to layer. Okay, so this kind of like given this kind of you can think of like ordinary differential equation on a network based model. And given this, you may need to learn the parameters from the data that is available. And here you can think of rho I may be an input data that you need to learn, or even the topology of the network in omega ij. So in this context also, you can have uncertainties, and say you want to minimize this difference between a output that is desirable and the network is to learn this term W. Sorry, the W gives a governing thing, and you may need to learn and the parameters involved. So here a yj, xj, yj, zj are the data points, and in zz you have this this parameters basically contained in it that you need to learn. So it becomes like on the network you have a potential driven. So you can see that this is a minimization problem. So I need to follow a this potential like a potential gradient approach before I fall into the like a desirable solution. But so the layered this network structure is now like we can describe in a continuous fashion with W dot and is equal to this minus the potential term, that thing, because you have this this energy kind of like this two norm square term there, so which you can think of an energy term. But this we want it to happen in a certain way, like in order to maybe to accelerate the learning, or to respect constraints that are there on the learning, and it can arise from many situations, including the topology of the network and all that. So this is also a situation where you get the DIE, differential algebraic equation. Now, more these things occur more naturally in path planning and control of robotic systems, drones and all these things, and there are lots of so since 1980s there have been lots of numerical methods for computing these things, including geometric integrators that preserve certain structure. It's like symplectic methods, they call it. And these are used in constraint optimization also. So, and more recently, these neural ODEs, neural SDs, these kind of like relate to this kind of modeling. So, any dynamical system basically that has a performance or safety or risk associated constraints, or topology even associated constraints to it, and subject to the constraints you want to perform it in a certain way or learn certain thing, gives rise to the DIE. So now, of course, these dynamics, if it is uncertain, that becomes a stochastic differential algebraic equation. Despite many applications for algebraically constrained stochastic differential equations, the literature is limited to this SD. So we wanted to study like if the constraint dynamical problem has a stochastic nature to it, like then subject to these uncertainties, can we still follow a path, follow a prescribed path or constraint? Okay. So I will try to be short, but so these slides are taken from my students' PhD thesis defense basically, but I will suitably, talk about it. So first we'll show, like, on Euclidean spaces, how we can approach these constraint dynamical systems with uncertainty, and then we can try to talk about it on smooth manifolds also. So a general model for SDEs on Euclidean spaces can be written like this. So you can think of networks or other formulation, other structure on which we are going to learn. And learning parameter is U, and X is the dynamics, basically the states that is involved in the network or any other model that we are talking about. So the model that is without the uncertainty is dxt is equal to FDT. So that so this part of the thing, and this is this basically it can be this F can be this network, actually this Laplacian and all these things. Now the uncertainty comes. The uncertainty term is added as a variance in this this you can think of dx is equal to F as a mean field dynamics, like a mean dynamics, but then if it is not satisfying exactly due to uncertainty in the system, then you can introduce a variance, and so out of the variance, square root of the variance term, that gives you sigma, and it is driven by a Brownian motion. So this noise, so dWt, which is a Wiener process. It's a standard Wiener process. So in this context, I can like mention that, recall that dWt is distributed as normal distribution, and at every time point, independent of each other. Its components also, if dWt is a d-dimensional thing, then its components are also independent of each other, identically distributed, but distributed as a normal distribution with zero mean and variance, which is equal to dt, that is the increment in time. So that is so the overall the scale of the process is root over dt. Okay, because variance is dt. Okay, now if you have a given data set, then and that has its own uncertainties. So you can see that if we knew the data set without noise, then the right hand, like left hand side, gx of gx comma u equal to 0 would be the equation for the the data manifold that I need to follow, and on which I need to project the dynamics in order to know the u, the train for u. But if you can have noise there also, and the right hand side gives that noise. So similar concept, like this is the stochastic integral is introduced in the Ito sense. So with the gamma, and you have again the noise that is driven by the Wiener process. Okay. So the central problem is to develop method for finding solution of algebraically constrained stochastic differential equation for learning in this kind of scenario. Okay. So now you can think of a problem in which like the number of algebraic variables is equal to. So we can always define as many learning parameters as there are data related constraints. That is m equal to p, and then there are some regularity assumptions, like so that solution exists, like a Lipschitz condition, a growth bound on the like on the in the neighborhood of the starting point at initial condition, and so on. Okay, and if you and also it is assumed that the initial condition is known with probability 1 and without noise, and then we can study the evolution of the dynamical system and how we can learn u given the data with noise g x comma u. So So here, so here it is actually subject to all these regularity assumptions. Similar to DAEs and similar to ODEs, you can build a proof for uniqueness and but here it is for local solution, because at every time instant U needs to be just learned from these for satisfying the system. U need not be global. Okay. So, so we talk about the existence of a unique local solution for the equation, for the model. And you can go in the same way as you prove for the ODE and with. So here we set up these, we assume that these are well defined, and so we go through well definition and finally have a contraction map. So the iterates. So iterates converge to the unique solution. So, so you have this. So you can write the equation as extend it. The G is written as a we introduce an extra variable Z, and then. And we set up basically a reduced DAE like a DAE like an SDE with a constraint, but noise is kind of eliminated. So this is the extended so basically the top two equations becomes an SDE, and you add a noise which is like a constraint, the data thing without the noise in it. So. So and once this is converted, you can go ahead and argue that is if the local solution exists, so then you can find an U at every time step to solve the. So once U is known, it just becomes the 11A just becomes a stochastic differential equation, and then you can use the usual tools from the theory of stochastic differential equations to show the existence of the unique solution. Okay, so here for computational purposes, we want to extend the classical theory of DAE so that we can apply the classical ODE numerical integrators that are reduced tailored made for the DAEs, and take a similar approach in case of SDAEs. So for DAEs, you generally have no noise and just the constraint, and then you can convert everything into a algebraic equation. You can see that. So basically, given the ODE, you can create. You can project the ODE onto the dynamics onto the constant, then you have the flow terms. So you can see the first flow term dxdt and then du dt, and this is 0. And A can be like if dug that Jacobian is invertible, then you can easily determine A, and this can be put back into the ODE. So, similarly for stochastic differential algebraic equation, and you can reduce the thing. So basically, modify U like we did here. We put a dynamics So this is actually a kind of like relaxation, because ordinarily we don't have anything in the constraint in the equation 12 that is saying that ut has to be differentiable with respect to time, because it is local and it can be just continuous, and that should be sufficient. But in order to ease the weaken the solution, because sometimes you may have a very noisy output of the ut, which is useless for learning or control. So ut is assumed differential, and this smoothing has been assumed for u, and then 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 this basically this is a rate of change of the control parameter or the learning parameter is solved for and put back into the put back into the equation in a fashion of ODE. So the same approach can be taken for SDAEs, stochastic differential algebraic equations. So here it is even more needed because if we do not assume like some kind of regularity, some kind of smoothness for some kind of structure of the solution for UT, the local solution can even be not even stochastic, but even can be a rough path. Okay, so due to which we may lose completely the regularity, and for an engineering point of view, from a computational point of view, the solution may become useless. So what we do in order to find a solution, we try to determine U in the following format. So that DUT is equal to ATDT, which is the drift term, and the diffusion term or the stochastic term is BT/DWT. So then, obviously, using the Ito calculus, the constant is differentiated. But note that when you use Ito calculus, as you get an extra term due to the Ito lemma. So you can see that for when we have like a deterministic calculus, everything is like just the first order calculus, like dx, du, and so on. Okay, just the first order calculus. You don't have a second order term involved because it is because with respect to the first order increments, which are of order of dt, it would be higher order and not applicable to the, like it would be too small for the calculus. However, here DWT, since DWT is distributed with normal distribution with zero mean and dt as a variance, and its scale is actually root over dt. So any DWT square, that means any second order business, any quadratic term involving DWT, then becomes important because it is of the order of dt. So you can see that unlike the deterministic, expansion, deterministic perturbation, you have the deterministic terms like same the dxg and dug. These first two terms are same as the ordinary dynamics, ordinary differential equation. But then, and you have a second order thing which comes from dxt transpose dxt. That is the second order term in the Taylor series expansion, which is now important and contributing a dt a term of the order of dt. So you have this half dxt transpose dxt. So that gives this half trace of this noise term, this drift, so diffusion term sigma, so this gives rise to this, these terms. And then since we want du to be in a certain way, so we have the expansion, and it is just a matter of finding the Hessian and then properly putting it in the expansion. Okay, so then this complicated term is so now we have an extra term, let's see, which is driven by so even in the deterministic part, the dt part, we have an extra term here. Now this goes a long way because your extra term may actually can have a benefit also. It is it can destabilize your ordinary differential equation used in some cases. On the other hand, in some cases, this has the probability of stabilizing in the ordinary differential equation. And of course, as usual, the noise term is there, and this is also satisfied. So to obtain U, now we have two equations. we have to satisfy the coefficient of dt and also satisfy the coefficient of dwt to 0. So this is the thing, and one can roughly can compute the solution like this, like with this simplification and thing. So you can define A like that and B like that, and basically you can put it back into the into 15 and 16, but now you don't have any constraint, so it becomes a regular stochastic differential equation which can be solved numerically. So one important thing here is that we need the Jacobian with respect to the Jacobian of the data manifold or the given path, whatever it is, the given data manifold, with respect to the control or the learning parameter u, that Jacobian needs to be invertible. You can see that in the formulation of A, which is put back. So A is the drift coefficient, and in the learning parameter. So you can see that the learning parameter can be evaluated only when you have this Jacobian invertible. So and there's an assumption like so you need to introduce as many like as many learning parameters as there are independent data conditions or data manifolds or data curves are there on which you need to so you need to match the dimension of the data manifold on which the model, that is the this stochastic differential equation, which you can in turn think of a layered network with a lot of layers, like each layer being like the time step to be projected. So basically you have to match the dimension m equal to p minimal, and then of course the condition number has to be very low in order to. But if we cannot have if you cannot introduce the learning parameter in the data from where you are learning, then this method is not useful, because then this like trivially the Jacobian is 0. Okay. So we can say that this. So there is a concept of index, like which indicates the ease of solving the equation, that learning model. So with respect to that, we can now classify that if you can have a invertible Jacobian and of the given constraints, the data from the data generated from the data with respect to the learning parameters, DUG. If that is invertible, then we call it an index 1. That is very nicely, easily solvable stochastic differential algebraic equation. Else, we call it high index. So now without loss of generality, because we have shown that the noise in the constant can be absorbed in the ordinary differential equation model by rewriting it. So, and trying to find a solution for this. So we can just put it in the formal mathematical language that which basically says that the condition for the invertibility, because so only if the image space is in the image space of the noise part, that both in U and X, that is the sigma, or technically called diffusion part, sigma and P. If the image space from this matrix, from this basically this maps, the image space is in the column space of the image space is the column space of it. So this is basically the condition for the invertibility of the thing. Then we can solve it. So this is from linear algebra. Basically, you can go back and see that why it is happening. So you just need to get this thing solvable, this DUG inverse, dx and df thing. Okay. So now we can take a geometric view of the problem. So the control or the learning parameter is also written as a stochastic differential equation for regularity, and then the constraint are generated by the given data or the requirement for control. So GXT, UT, and that is kind of differentiated in the stochastic sense, and then you get a drift part and more importantly a diffusion part. So basically, then the diffusion part, for the diffusion part to go to 0 is obviously this part has to be like dx, ug, this Jacobian, and should have null space, and basically that sigma b, that other matrix, must be in the null space of that other Jacobian. So that's exactly that image space of sigma k b k should be part of the kernel of that dxug. Okay. So so geometrically we can state that if at the G inverse at the initial point, if it is S, then the tangent at the S must belong to the kernel space of the thing, so that the noise disappears, and you can solve the parameter from the drift part only. Because essentially what happens, like you have this u is like only one parameter, like one vector parameter that you are solving, but you have two conditions. You can see that from the drift and the diffusion. So it is needed that it is essential that the drift part kind of neutralizes. It is designed, sigma and b are designed in such a way that it basically neutralizes, like it makes it null, the noise thing. Okay. So then you have a high index stochastic differential algebraic equation, and in the canonical way, and now we consider the form in which we cannot insert the learning parameter or the control parameter in the constraint. That is the data that is given to us. Okay. So as I said, I mean, like I will, throughout my talk, I will refer to like two situations. It can be GX can be from a data. The constraint from me can be from a given data on which we are learning, or it can be a prescribed path along which the dynamical system should go, like in a control fashion. So you can see that like actually this control theory and informatics, and then learning has its like this classical relationship is there. You can show them inter alia, like like kind of dependent on each other. So there is a link between all this control and learning. So in the 1960s, this was viewed as cybernetics, that when initial robotics problems were solved. So anyway, so we consider the high index situation in which I cannot insert my learning parameter or control parameter in the constraint. So so this is like if you are familiar with mechanics, so you can think of like a particle that is that is forced by noise, in addition to its usual drift, and you are requiring the particle to go along a prescribed path, and this path is independent of the control parameters there. So this path is related to the position of the particle alone and does not involve the control terms. So this will have a solution if you have this. So if you are looking at a tangent space in the neighborhood of the consistent initial condition, that is G inverse 0, which is called consistent initial condition. So if the diffusion is in the like the image space of diffusion is a subset of the tangent space at the initial point, then we have a solution. So that's what we found. Like this can be showed as a corollary. I'm not going into the intricate things. So we're trying to present it in an engineering manner here. And if not, then it becomes kind of like difficult to solve, like difficult to say something about the existence, even existence of the solution. So the equation of the power in the form of 20 we would not consider in this study. Okay, so you can basically make this contrapositive statement, and basically this by showing that the second corollary is ill-posed. Okay, so for solution, for a useful solution to this, this learning problem or the control problem to exist, sometimes you may need to actually relax the SGAE. So, especially when it is of high index and you don't have a direct solution, like a direct way of computing the solution by computing an inevitable Jacobian. Especially then, you need to relax the problem in order to get a reasonable numerical solution in a useful and reasonable numerical solution in a reasonable time or reasonable computational time. So what we do, this is a computational artifact. We have presented a straightforward method for index 1, but for higher index, we need to do something. So generic form of the relaxed high index SGAE almost surely can be written as in the form of equation 21. So here you can see that instead of saying that gxt equal to 0 at every point, like every time point, I'm relaxing the constraint to say that, okay, some error, accumulated error, like some error in some norm, that is a violation in G, will be bounded by some tolerance, some epsilon. Okay, so you can see that this we often do in our competition, because we cannot have a exact 0 for an iteration or things like that to converge on your computer. So it's a similar kind of like relaxation. So for solution, what we do is we try to introduce a function y that goes like essentially which takes time and m-dimensional input and gives it on an m-dimensional input and gives it on an n-dimensional. So the m-dimensional input is the learning parameter and r is the time thing, and this produces the output in the state space, so x. So if you assume that, then you can set up this dy dt, then becomes del u del t, and then of course we have to have a flow term. So this is the first order flow term, and from this you can so if you know the dx dt, and you can set up the because the dx dt is f, so you can set up the partial this partial derivative with respect to time to equate to f minus d2, and with the condition that at every time point it would be equal to xt. So you can see that this is a trick on the for the relaxed AE to be solved. And in the step 2, basically the G is introduced. So you do the same thing on G, and you get a different like this flow thing on the given constraint. So next step is to freeze the dynamics at time t. So that you want to define a rate of learning, that is this u dot t, and provided this term, this dg, like this derivative, this Jacobian of g, a so the Jacobian of g, and in which f, the f is an input. So provided this thing, and you can see that, and Jacobian of y with respect to the second parameter, that is z. So if this is invertible, then we can set up a solution, and from this del g del t is equal to 0, because we need to have del g del t is equal to 0, because we need to approach the constraint. Okay, so you have to make it as small as possible in violation, as small as possible in time. So so in fact, this is actually very like a different condition. You can see that now we still have a Jacobian invertibility condition, and still sticking to us, but this is not with respect to the learning parameter. Okay, so all in the state space. So if you start from time equal to 0, and if you start the y initial point such that it satisfies the constraint that that errors are less than epsilon, then u dot t can be solved, and you can find a solution that is consistent with the given error condition, that the relaxed error condition on the constraints. Okay. So in case of SDE, so this trick is for the high index DAEs, but then how do we extend it to SDAEs, which is no more, which is the problem at hand, and which is more likely in data science. Okay. So we need to use the generalized Ito formula for SDEs to find a vector field A and B such that the solution XTUT is given by the certain SDE. So we are modeling the learning parameter into an SDE, and so it goes like this. So same thing, but now we will have extra terms. So so if you have the error tolerance, and then so you have to expand this in the so the constraint G is now expanded in a Ito fashion, which has this. You can see that you can go back and show you that the trace terms are there. Half of the trace terms are there here. So you can see that this is now extended. So you will need to take care of these extra terms, and this is exactly what we take care of when we solve it. Excuse me. So you have these extra invertibility conditions, and because you have to keep the diffusion terms also to 0, and along with the drift term. So there it was just du is equal to ATT. But here it is, the B is also there, so it needs to be solved for that. So one can write down the thing and equate the term by term, and from the general Ito expansion, if after applying the Ito lemma, and then you have this, these things that have to be solved, and these are basically nonlinear equations. And so with this modeling on the learning parameters, we solve on the so some of the learning parameters now we have to set up like that. So we solve it from the constraints by setting it to 0, and after that so this is the initial condition basically. So once the initial condition is needed, you can see that now for x and u, you have both have initial condition. And if you remember that initial condition is like G inverse 0, so that is the tangent space where the dynamic starts. And so the number 4, line number 4 is just the initial condition. And once this is found, and once we use the terms from line number 3, this is all put back into line number 5. You can see that now it is just a ordinary stochastic differential equation. And these things can be solved by, so these are expensive to solve actually. And people generally use the simple Ito method, so the Euler method, just the forward Euler method, which has a strong order of convergence of just root over the time step, not the time step. See the forward Euler method for deterministic systems has is a first order method, like first order accurate method in time step, but when you have noise, it becomes a root over of the time step. So it is the order becomes the exponent becomes half only, root over delta t. Okay, so but you can take small time steps and still solve it and get a useful solution. So here is an example. It's a toy example. You can see that. So G is some. G is obtained by fitting some curve to the data points, and this is the this is the dynamical system that I wanted to learn the U, so that we know how to how to deal with the data that it is being applied for. So Gxt is the algebraic equation, U is the algebraic variable, Bt is the one-dimensional linear process, and you can see that G does not contain U, the learning parameter. So with this we solve the system with this algorithm that we have talked about, and you can see that. So this is like X versus the time plots. For SDE, so with no learning parameter, the white dashed line indicates the algebraic equation. So we are supposed to come into this manifold, but we are far away from it, and you can see that these are the noisy paths. But there is no learning yet. Okay, so we have to show that how we are learning. So the colored lines show that it's a XT versus BT plot for different realizations. So these are like you generate the random numbers and you let them go, but we are far from the these contours of the constraint manifold that given by the data. Okay, so this is we use this this forward Euler method with a small time step size 10 to the power minus 4. Now. Now we use the SDE, and so we have the constraint, and the black lines show the bounds on the constraint. So you can see that we allowed it to be relaxed a little bit, the epsilon thing, and the colored lines show the plot for different realizations as usual. You can see that. So the numerical integration is performed with Euler-Markov, but you can see that now we have a tendency, because UT is now activated, you can see the tendency to follow the one of the contours. You can see that if you look at the zero plot, you can see the white lines actually hidden behind the dynamical system, because now the U is learned in such a way that we are on the E data manifold. So you can see that this is untrained, and you can see that it is going wherever it wants, and this is with training. So we are achieving the training, and we are matching the the contour required by the data set. So if it is high index SDE, then can we solve with some bounded probability, so that because not always even this because this is a stochastic system and we need to give some guarantee within in what error bound we have learned the the dynamics from the data. Okay. So in previous algorithm, choosing the function is a challenging task. Therefore, we relax the problem further, and we see the solution, and with a bound error probability bound. So the relaxed form is this. You can see the equation number 24a is just the dynamics with a drift term and a diffusion term, sigma. And here we bound the probability between some 0 and some alpha. Okay. So, or you can even put like, another, between some alpha 1 and alpha 2, for example. So you put in, like you want a guarantee, solution guarantee. So alpha is, of course, like you can take it like you can take a lower bound and the upper bound between some, say 0.8 and 0.99 or something like that, so that it is learning almost surely. So if you differentiate G, as I pointed out earlier, that this introduces the diffusion term now due to the second order property of the Brownian motion. It introduces a half of trace term into the drift of this, this dg, that is the small perturbation of G. So the small, this instantaneous increment of G, the constraint. So this contains this half of the trace term and the flow term in the usual flow term in the diffusion. So obviously, to make this thing 0, we need to equate this thing. So if you have the drift is equal to minus bgx, and so if you write it as a b times gx, and then reintroduce it into the differential like an SD involving G, then one can show with the Dupes Martigan inequality that we can probably find a large enough B so that the probability bound is satisfied. So you can think of like a relaxation in which we have allowed it to be like a Lipschitz quantity, and you are allowing a large enough Lipschitz coefficient, and so that the probability bound is satisfied. So the algorithm goes like this: define A as to be this Jacobian of the constraint multiplied by the post multiplied by the diffusion coefficient of the model, network model or anything, and let J be the supremum over XU for this trace of A transpose. This term comes from this the second order terms introduced by the Wiener process. Choose a B. We have to choose a large enough growth, basically allow it to grow in a sufficiently in a sufficient rate, allow it to have a large growth rate. So B is chosen as such, and then define the so you can see that this is the drift term. Basically, this is the drift term from G plus the BG. So you want this to be solved, because we have set up like this is equal to some Lipschitz like a growth factor into G. So we are going to solve it for and B is like a sufficient growth factor here. So it is parameterized now, and H has to be solved. You can do it for like with a Newton iteration, and then once H is solved, you get your B and you plug it back in here and solve the stochastic differential equation. Okay, so so here is an example. We have say we are at the origin with probability 1, almost surely. From data, we have this, the same curve that on which we want our solutions to be, and we are employing a quadratic, like a quadratic kind of device in order to, like, quadratic function and all that to learn, and U is the learning parameter. So if you have a one-dimensional thing, we again use the Euler-Marigau method with a 10 to the power minus 6 accurate, like as your time step, very small time step in order to ensure accuracy, and also the stability, because you all know the forward Euler method is not very stable. It has just a small circle as its stability region. So, so algebraic variable is also 1, and it is a one-dimensional just a curve as your data set. And data set is just interpolated into a curve. Okay. So no control. Okay. So first there is no control, no learning. You can see that without any learning, the black dashed line is the bound on the constraint, and the colored lines, which are the different realizations of the dynamical system simulation, it goes everywhere. That So you can see that it does not. So you can see at 0, you can see the black line, which is the constraint, and it is not on the constraint. It is just traveling anywhere, and you can see that sometimes it may travel outside, right? Travel outside the that whole dynamical system, because it's all random number generation, right? And Brownian motion can take it to a different contour in the contour line of the constraint. Okay, so now the situation improves. The white dashed line is the constant. So this at 0, you can see the constant is now almost hidden behind the realizations, because the realizations in the so this is in the probability bound. So they are all very close to, like, in the neighborhood of the constraint, all the realizations, because with the learning parameter is also activated. So we can learn to be almost on the constraint, almost on the prescribed constraint curve. Okay. However, sometimes you can. So this is noise. Okay. So this is. So there is. So when you have the Wiener process, there is no bound on the Wiener process actually. So the Wiener process can occasionally take you far away because of the like you are generating random numbers, and so it can sometimes take you far away from the constraint. But when it goes away, you can see that we can be on a different contour line of the constraint, and basically switch the contours, and still we can try to learn on a different contour. So so this is very this is an important thing, because you can somehow, like, if you are even with high noise, or even with some unpredictable instability that you have in the dynamical system, you can still recover and be at least learn to be on some be on the contour of the constraint that has been prescribed. So you can see that this blue, so this purple thing has come down. Excuse me, and it has hit a different contour line, but it was still on the constraint. This satisfies the constraint. You can see that. You just have a switching, but it still satisfies the constraint. Okay. So here epsilon was 1, and you can see that relaxed in a constraint. So the probability that it exceeds the relaxed constraint, and so this probability thing is given in the form of the Chebyshev inequality. You can see that. So alpha is the Chebyshev inequality, that term of the probability term of the Chebyshev inequality that you can introduce. So yeah. So you have more, like, if you reduce the violation to only 0.5, and So this is as usual. This is x versus the v. This thing, and so x versus the time thing, and you can see the simulations are there, and for 0.5 you can see that we can actually restrict it to a, although it is noisy, and there is an increase in the that small the faster manifold, the T frequency thing, you can see that. However, it is still on the manifold. You can see that it is, and translation into a different different control line has not happened here. You can see that this is it's noisy and it still is on the so the violation, the constraint is tighter, and now you can see that we are learning better from the so the model is better, like you were estimating the learning parameters much better. So with tighter constraint, we can see that we almost converge, even though it is noisy, almost converge on the constraint. Okay. So if you come back to that gravitational, that basically that potential driven problem, then you have the potential plus some force in it, that is the learning component, and then you have the noise, and you have the prescribed path to follow on the 2D plane. And this was our DAE solution, where now if you have u equal to 0, it can go anywhere. But if you activate the learning, you can see that it can basically follow the constraint, that path, and come to the the center of that gravity, where the particle which due to which the this potential field is existing, basically. This force field is existing. So this is a potential driven. You can see the force is the gradient of the potential, and you can see that how it will go follow the spiral and fall into it. So then another example problem. So so this is if you have so the force is the now so this you can see that it is like a divergence term on the right, and driven by by its own weight, so the body force, and this is the this is basically the so 29 gives that divergence, basically divergence driven and thing, and divergence plus the body force that constitutes the momentum here, and you can drive the particle with it. So the error term is now so you can see that on 30 there is an error term, say is it the modeling error, it can be, and this can be represented as a Ito-stochastic differential equation. Sorry, Ito integral. Sorry. So with gamma ij as the diffusion term, the kernel, and dwj is the driving noise, the inner process. So this also can be solved similarly, and basically one interesting thing is that if you put the divergence of sigma ij as a gradient of pressure plus a diffusion term, diffusion of the velocities, and with so this is the inertia thing with the with proportional to the multiplied with the viscosity parameter. So then, if you put that back, then the same model 31 can and kind of give you the Navier-Stokes, incompressible Navier-Stokes kind of driven thing. So basically, if you have a flow-like problem, so flow networks are becoming popular nowadays, and if you discretize something like this equation 33, you can get a flow network, and you can learn on the flow network. by suitably introducing a control here, okay, or a learning parameter here. So you can see the 33 thing. It's a modeling artifact. So dynamics of a particle in the fluid, it's kind of a Lagrangian formulation, and so it's there, and with a three-dimensional Wiener process, because it's in a 3D space. So any direction the particle tries to move, you have an uncertainty. Okay. So this equation is coupled with the position of the particle, which is given as this thing VBDT, and using Stokes law and additive type noise, you can finally write a different version of it. So okay, so this is like punched with Stokes law. You can have a different version of 33 in 34. Okay. So without loss of generality, you can write these things as Pp plus epsilon, and then this momentum thing for the position, because the Lagrangian formulation, so position plus some error term, not exactly the velocity it produces because there is unknown dynamics, and then similarly an unknown momentum thing, that acceleration term. And if you want the particle to still follow a desired trajectory, then it becomes an SDAE. And obviously here one has to find out, like for example, you can introduce this epsilon or CI. These will be the like parameter, or gamma. This can be like the learning parameters here. So if you have epsilon in the form of here, the form of like some proportional to some gradient term, like in a gradient of a potential, then you can then have lambda, as a learning parameter, and you can kind of like determine it here. And for algebraic, like for SDE2, like where you have higher order, like higher index SDE, it becomes a little bit complicated. You can see that all these Hessian terms and things come in. Okay, so here is an example. So constraint is just an exponential of x1 plus x2 minus x2 is equal to 1. And initial condition is known surely. A velocity field is given. And we want to solve for it. So here is the fluid velocity. So simulation, like, after performing the simulation. So here, these things are assumed to be known, and with these parameters, the gamma is already known. We are not determining gamma. You can see the velocity fluid velocity field can be computed. This is straightforward. Okay. So if you follow the trajectory of a single particle, of course, this will be like in various realizations. This will be noisy, as expected, because it's driven by Wiener process. So here, if you want to control it, like if you want to follow it, this constraint path, then you have to choose basically you have to solve for a learning parameter which makes this possible. Like instead of all these things, the particle moves in the moves on the curve that is prescribed. Okay, and so the lambda, this thing that is helping us learning, and that is extremely noisy. You can see that, and for 100 realizations, it captures the Wiener process, the noise driven by the Wiener process. So these are trajectories with perturbed initial conditions, and you can see that we can still catch up on the prescribed path. Same problem, but different initial condition and constraint. So here you have a constraint thing, and as usual, the white line is the constraint, and we want to capture it. So basically, it's a perturbed, initial condition, and we slowly come and catch the manifold. This is very important because you may not always start from right on the manifold, that is the data manifold, because you may not be able to determine the learning parameter initially. So it is important to come back on the manifold, starting from away from the constraint manifold or the constraint curve here rather, and to come back on the curve and with your learning parameters. That's very important, and we have done it here. And this is the higher index, and you can see that here there is a necessity to start from the on the manifold, because otherwise so there is a consistent initial condition requirement here. Because if you remember, it is the G inverse 0, that is the tangent space of the G inverse 0 from where we need to start. And however, we can learn, and we can basically we can learn this noisy learning parameters. We can solve for it and still be on the white line, which is our prescribed path, that prescribed curve generated from our data. So, so I'll be like short on it. So this is, so we'll be closing. So I'll just give some. So this is the main thing. So this is an advanced topic. We derived some relationships that was like for the first time, and basically we derived a new Ito formula on manifolds. But I will not go into all these things. I'll just basically before closing the talk, I will just give you a hint. And these are like kind of like one of the, if not open, but kind of like a problems at the cutting edge for data science. So stochastic differential equations also can be on manifold, because data will not always be a curve on the Euclidean plane or hyperplane. So if it can be a manifold, and these stochastic differential equations on manifolds, because you have this dynamical model, maybe you build it up with a network or other, just by writing the equations for the layers, in the neural net or whatever way, or just using some functions, or sometimes they're called these differential equation networks. So you can formulate them as Stratinovich SD. So Stratinovich calculus is a variant of the Ito calculus, but with correction terms in such a way that this second order, these quadratic things are not needed, and it follows our standard Leibniz rule in our standard first order calculus. And then there are operators, little bit advanced thing, Schwartz operators, and so which you can think of like a transform, like a second order term, like a diffusion term, like an advection diffusion term, which transforms a input into an SD, like a noise input into a stochastic differential equation. So, so what we did here is like this find this kind of formula, basically. So where on a manifold M that we have this coordinate invariant for this is a Stratinovich. So you don't have to worry about the second order terms. So you can write like this, and you can have the models. But now you are on the manifold, so you have to be careful. And so this DXT and all these things have to be related to the actually the geodesics on the manifold and connections on the manifold. So here it is written like simply, like if you say have a connection, you can just write like that. Okay, so the more important thing was this. This is called a diffuser. So you can see that this is just like a like a first term is an advection term, and the second term is a diffusion term.
Sir, we can close. We can go for
just two more, and I will just So
yeah.
So with that, we introduce some new calculus, and basically find this this kind of thing. And it is important to have these perturbations if you want to capture, like learn on the manifold. So okay. So with this, like so I will not go into all these things. So this is like the slides are there, and you can follow up later. And so I'll show some simulation that will be more interesting. So you can see the white line is from the data, and it is on a sphere. And you have this vector field is a dynamics field, and this is so this gives the the coordinates basically on the dynamics, and this is the geodesic. Basically, this shows the geodesic directions. Now you can see that we have this dynamics simulated. So this is without the control, but as we learn, we can learn it like as we learn with stricter and stricter constraints. So you can see that even on a sphere, even on a manifold, we can basically learn a model according to the prescribed data. So you can see that you can make it better to some extent. So that is the talk, and I will close it here. I hope I could arouse your curiosity about this constraint dynamical system approach to learning, and building maybe machine learning models from it, and or controls, other things. Thank you very much. So Nachiketa, you can open the field. Yeah.
Yes, sir. Yes.
Yeah.
Thank you, sir. Thank you, sir, for this kind of challenging research topic on stochastic DAE. Basically, there are a few things that I would like to know. So one thing that we have just now seen the first beginning of that SDAE, that what we have started in the index 1. So I think this is the past study. That's why you are going for index 1 study. That's what.
Yeah.
And sir, index 1, most of things like we have observed, both of us, like the index 1 can be treated as like a perturbation method, and can be introduced a derivative with the term and can transform to the system of OD, and epsilon tends to 0 case can be done in the solution. Is that same for the SDA also?
Yeah, I mean, notionally it is same. Only thing is that you have this Ito formula which complicates the thing. So you have an additional diffusion term to take care of, and so that's why we did some of this. This basically some manipulations, you can call it, because to match the like the null space and all these things in order to bring the solution there. So yeah, so what happens is that for index 1, you can introduce that learning parameter or the control term directly into your constraint. You can write your constraint that is generated by either the data or a path requirement in robotics, for example. Then and you can solve it directly. So without the help of the dynamics, without going into the dynamics, you can kind of solve it and put it back into your dynamics. So in reality, index 1 behaves like an ordinary differential equation, just like a unhindered dynamics, like once you put it back. So the effort, computational effort is very little in index 1. The challenge comes from the higher index, and also these restrictions like on this invertibility and all that in higher index. And with noise, of course, we have to deal with the diffusion term always, and so that we don't have an unrestricted solution of the learning parameter. So that is exactly what we wanted to try to do here. Basically, use some this manipulation of the thing by writing down the terms in a different way, so that which is makes computation easier, and so that at least where the invertibility of the required Jacobians are available, we can at least solve the higher index problem. So unfortunately, the higher index problem is more common in data science and control, because for a robot, for example, the path in terms of positions are generally specified.
But sir, anybody has done high index for SDA? People have done any...
So we did that, but then it becomes a limited problem, because now you have the diffusion term. So not every problem is admissible. Every problem has an admissible solution. Okay. So you can see that. I can go back. So you can see that. So this is what we are proposing, and you can see that. So you have to like this is the index one thing, and if I come to the slide slow, then it is better. So you can see that this is. So you can see. So this is the higher index SD, number 17. Okay. So you want to learn U such that your constraint given by the curve given by the data, Gx is equal to 0, is satisfied.
Okay.
So there it becomes some, because the issue is this invertibility, because you are now, if you determine dg, like if you give the g a little bit of perturbation, then it is in the Ito sense, and you have the quadratic terms coming into the thing, and that makes this, these conditions. So basically, you have to solve for a and b, two coefficients, and the first equation is given by this dotted thing, this basically this drift part, which can be solved provided you have a restriction and on the null space. Like you have to choose your B in such a way that this null space is satisfied, because you don't want or the noise becomes very small, and the drift part is So this is the condition basically. So the solution is B for the learning thing. So the learning dynamics. So B and sigma. Sigma is the uncertainty in the dynamics, the dynamical model that we have done. It can be from the network also. So the image thing should have the kernel. So it should be in the kernel of this thing, dxug, and.
So that that image thing, when you talk that in the subset of kernel.
Yeah,
I mean that DUG, that what you are taking the kernel, is it that is there any assurance that the kernel will be non-empty? It may be empty separate.
Yeah. If you, so that is the restriction. Like you cannot solve everything. Okay. So only when you can design your learning like this, then only you are able to learn. So it becomes a more restricted problem. Okay. But unfortunately, these kind of problems exist in the data science. So, so here this is the restriction. Like not anything will work. Not any solution can be admitted, or not any SD can expect. You can expect to have a solution. So this is one of the things, and then of course you have to solve for A and B. A of course. So to solve for A, you have to have the last condition, because so this is nothing but equating the drift term to 0. Okay. So this is the thing, this is the restriction. So naturally, you can see that, with more noise, you are being pulled out, right, of what you want to do. And also you do not have a direct way to learn the data. Like, so Gx is nothing but it's a curve given by your data. So, and not having the learning parameter in Gx, means that you cannot learn directly from the curve. So you cannot have for example, you cannot have a parameterized curve or something in which you choose a parameter and you fit what you want to fit. Okay. So it is a indirect scenario and noisy scenario. So you can see that that not everything will be admissible. Not always will be able to learn it.
Oh.
Yeah.
I mean, so that page number 21, there is the algorithm that you framed.
Yeah.
So in that case, I mean, the learning rate that you control is basically the learning rate comes in the Newton iteration, or which learning rate you are talking about?
Yeah. So no, the Newton iteration is just to solve the initial condition. Okay. The initial learning parameter state. Okay. Because you can see that this is everything exists in the neighborhood, like So you have to start it from the neighborhood of the tangent span, and S is defined like G inverse 0. That gives the S. So in the tangent space of the initial condition, things start. Okay, so this is to capture that thing. So it is nothing but, so just a second, it is 21, I'll come to that. Yeah. So, yeah. So that is exactly, so this is called, so step 4 is typically in computational jargon, it is called finding the consistent initial condition. Okay. So that you satisfy you are on the curve, on the constraint curve that is given by your data. And then you start, and then this number 3, all these relationships these ugly looking relationships are derived from that, those conditions, like by expanding G in by Ito lemma, and then equating the drift part and the diffusion part. So diffusion part, we need to make the 0. That kernel thing is there, and also this drift part, we have to make some equations out of that. So this is just just by batching terms actually. So no great mathematics in it. So after that, you feed that into that. So once you have a complete, you have a viable SD which you can solve, and this solve by number 5, step number 5. This rather higher dimensional stochastic differential equation is purely numerically solved in order to find the like a bunch of like paths for the learning parameter. So these parameters, like once you find sufficient number of realizations or paths for the learning parameter, then you can characterize it. You can talk about a probability distribution or its mean path or other things.
Okay.
Yeah.
So I think we are
Hello,
just
sir.
running short of time. One participant can ask one question only.
Yeah.
Sir, in the model, there is a constraint, right?
Yeah.
So, epsilon is we can treat as a learning parameter.
No, epsilon is just a relaxation. So not everything will be solvable easily. Okay. So you can relax. So this is like the relaxations of the thing.
Yes, sir. As you said, no, sir, if you decrease the epsilon value, so constraint will be reduced.
Yeah.
So model will learn nicely.
Right. So if you decrease the epsilon, it becomes tighter. Yes, it becomes harder to solve the problem. Yes. So for some problems you may not be able to solve if you take epsilon to very small number like a 0. Okay. Yeah.
Okay.
Yeah.
So is there any optimal value, sir, we can take? Epsilon?
Yeah. So if you set up a so that is exactly like that is one model we discussed, this toy problem. So you can see that. Just let me come into the slide slow model. So yeah. So yeah. So you can see that. So this is exactly how we basically converted it into a like a basically a stochastic differential equation
Yes,
and a flow problem. Yeah, you can see the flow problem. You will kind of get your answer in the flow problem.
Yes, sir. Yes.
Yeah.
Thank you, sir. Thank you.
Okay. Thank you.
Okay, so we are running out of time. So, if any other questions by the like the participants, they can just mail me, or you can mail to Professor Raha already. You can know that he has a nice home page in IISc CDS department. So you can directly interact with him also through mail. And let us thank Professor Raha here for this nice talk, and particularly very technical and very advanced kind of data science topic. So with this, we once again thank to the Professor. Thank you, Raha.
Yeah. Thank you very much, and you are most welcome to to get interested and on this kind of topic. Thank you very much.
Thank you, sir.
Okay. Okay, I'm disconnecting. Thank you.
Yes, sir. Yeah.
Okay.
Okay, so now we have second speaker already present here. So let us once again come back to this all participant again. So for this session, we have Dr. Arijit Ukil as the guest speaker of this session. Before he starts his talk, let me take the privilege to introduce him. Dr. Arijit Ukil is working as a principal scientist in TCS Research, Tata Consultancy Service, India, with expertise in area of deep learning and expandable AI. Prior to joining TCS Research, he was a scientist in DRDO, India. He was published 60 research papers, authored 6 book chapters, filed more than 50 patents, and 40 patents granted worldwide. He holds PhD from University of Murcia in Spain. He was a keynote speaker of IIITDM in 2016. He is general chair of KDAH workshop and ACM CIITDM 2018 to 2023 and ACASSP 2024 workshop of deep neural network model comparison. He is one of the speaker of IEEE ACASSP 2024 tutorial titled Sparsity in Large Language Model, the new Odyssey. He is a senior member of IEEE. With this small introduction, I hand over this session to Dr. Arijit. So, Dr. Arijit, you can please take the session.
Yeah, thanks a lot. Okay, so it's the second half, and we have very detailed discussion, maybe more technical discussion at the beginning. So I'll come with some lighter note. Okay, and let me share my presentation. Is it visible?
Not yet, Ken.
Is it visible now?
Yeah, it's appearing. Yeah, now it's quite appear. You need to make the full screen.
Yep.
Yes, sir.
Okay. Thanks for inviting. So it will be a bit less challenging, or say a bit lighter than the previous, the way previous speaker takes up the topic. So this topic is more kind of a a practical or real life way of AI. So the topic is AI at edge. And why AI at edge? Because we need some model optimization techniques for deep neural network. So my name is Arijit Ukil. So I already been introduced. So I work in TCS Research in India. So that's same thing. Okay. So let's come to the point. Sorry for that. So why we're all discussing this? Because we all know what human capability and machine capability were there few years back, maybe a few decades back, and now it's completely changed. The way it changed maybe decades back and the way it changed in decade is different. So that's why we are so much interested in AI. And one of the biggest reason is this LLMs or these foundation models. So if you are as a researcher in machine learning or artificial intelligence, so if you are following that trend for last few years or few decades, there are different researchers, even some of you heard of theoretical researcher Bernard Skolkoff. So they, at least few years back, maybe not few years, maybe 5, 6, 7 years back, they were very much in a dilemma to say that AI exists in generative domain. AI exists only in discriminative domain. And that's why the interest of AI was very much limited, because human beings are more in the race of generation. That's why we are unique than others. And what is the landscape change with this LLMs or Gen AI? And the way things are moving, this is a kind of the number of parameters. So all things are parameterized. So we have a model which is defined by a set of parameters. So that way this machine learning or typically deep neural network or neural networks or any machine learning network is defined by a set of parameters. The surprising thing happens is last few years where it took exponential curve and the number of parameters have increased in a larger extent. And you all know the story of GPT and all. So these are billion parameter models. Now they are coming up with trillion parameter model and mixture of experts, which are basically X, say 8X. Say if you have a Mistral 8 model, there are 8 LLMs basically together, and they make a one fundamental model. So it is in trillion, the number of parameters. So then what is the benefit we are getting? We are getting a kind of intelligence which is never thought of. But what is the, is it what we want? So we in a human way, we are thinking in a larger perspective, but the way we take our things, it becomes smaller. So if you see our computing domain, it starts with, say, traditionally it starts with some bigger computer, maybe beyond PC there were some mainframes and all were there. But after that, personal computer took a long time to settle, and then it settled in our life, in our drawing room. Then came the mobile computing. So this is everywhere now. So things are getting shrinker. Now it is expected that next computation device, which is a mass use, will be much smaller than what if the trend continues. But here lies the problem. So that is a complete gap in supply and demand. So our supply or the hardware supply or hardware form factors are getting down in a mass scale. If you want to have a computation for the mass, the hardware supply is getting down. But the demand for computing is, in an exponential way, it is rising, mainly due to this LLMs and this Gen AI. So why all these things? I think if everybody knows, but the main part I want to point out here is that this is where things are changed, because this deep learning, where amount of data to be trained is equivalent to amount of intelligence. So that's why exploited in all these GPTs, all these Gemini, Llama. So they have trillion GB, or if you say, means not trillion parameter model. So there are some 1000 GB data over been captured and trained over that. So this is typical, so everybody knows. So now coming back very basic level, what we basically do, we do some kind of network design, then to develop some applications using deep neural network. Then we see that if it is working or the meets performance goals. And if it meets performance goals, then we trained with some with PC or say most probably a GPU. Trained network, even say it is meeting some performance goal or accuracy or other goals, then this cycle reiterates, and ultimately when we get a satisfactory model, which is trained model, then that is the translated model, that is the trained network. Then we deploy this network for some purposes, for some applications. This is very straightforward thing. Now coming back to our current problem or current intelligence at edge. So what's happening? So we may not be aware of. So we are basically surrounded by thousands of intelligent devices, be it in your mobile, be it in your car, be it in your transport device, be it in your medical equipments, everywhere, but we are not aware of it. But where lies the problem? Problem lies here, that we want to make it intelligent. But if you make it intelligent, the cost is amount of data to be trained and the size of the network. Because deep learning is all about that. So every domain, so in agriculture, space tech, means in healthcare, in transportation, everywhere, same problem arise. So basically, as from industrial research, so we know the industry problems very well. So there are different ecosystems where we understand what the problems are. So every domains are facing the same problem because they know that intelligence exists, but it cannot be deployed. And there are other factors, real life factors, like say in a supply chain management, or in some reliability is a problem, in medical implementation, medical device implementation, privacy is a problem. In some real-time response scenario, let's say automated traffic condition detection and all, so latency is a problem. And many of the cases, devices are battery powered. So now if you have to deploy these kind of models in a processing unit, so it consumes huge power. You know that nowadays it is estimated that 10% of the world energy is consumed only by these Gen AI stuffs, at least in last 1 year. So see how much it is effective in our world, in our life, that is debatable, but that is the amount of energy they are spending. So, but in real situations, we cannot deploy this high parameterized, over parameterized models into embedded system or into an edge device. So because most of the devices are battery powered, so if each microwatt is of importance, so battery budget or power budget is very limited. And also they are constrained by the memory, because the memory and all form factor, it is equivalent to the somehow if you have a more memory, there is some more computation will be there, and then there is a power consumption will also be there, and there is a form factor. So all this ecosystem, all these constraints now compelled us to think that this intelligence which exists in the world in deep neural networks, the way deep neural networks can be trained and they can be controlled or can be used, so that exists some constraint, we have to overcome that. So I'm just giving a glimpse. So maybe everybody know that cardiovascular disease is the leading cause of death in the world, in every country. Because most of them is that 1 in 5 heart attacks is silent. So many of you may be using some smartwatch, even in the many smart mobiles, it is that app is there. So we can basically capture electrocardiogram. That signal, that biomarker we can capture. And there are incidents from Apple Watch that using that, so Apple Watch has an implanted ECG measurement sensor, some life-threatening condition called atrial fibrillation was detected and a person was saved because that alarm was generated, and he contacted the hospitals and he was given the defibrillations and medications. His life was saved. So this is very important, because otherwise if we cannot deploy this intelligence for human centric purposes, ultimately it will be all of fun and entertainment. That is very useful, but that is not what it is meant for. So if you want to use it for real human benefit, then this kind of applications come into play now. But it needs less compute, it needs less memory, it needs less battery power, which current intelligent systems or intelligent models are not capable of. They do not basically care about compute, memory, and energy. Not going all this. Yeah. So if you have some wearable device, if you want some intelligence to be part of that wearable device, and you want to check your health, you want to check your heart health and take a decision by the wearable device, and that can be used for monitoring and some kind of screening and some kind of life-saving purposes, the models exist, at least from cardiovascular marker like electrocardiogram, photoplethysmogram. If you can real-time capture that using our some off-the-shelf sensors, even smartwatches. But the problem here is the intelligent model, which is of very, say, few hundred MBs of size, but that is not possible in this kind of small devices. See, you can see that even the RAM size is 100 KB at less, or maybe to 128 KB. Flash is 1 MB and all. So how is it possible to incorporate such intelligence in this kind of smartwatches? But these applications are very much useful and life-saving. So what I talk about is, here enters the tiny ML. So what we are talking about in a theoretical or statistical learning perspectives, the ML community, or say the extended deep learning community, they are more inclined towards making a very sophisticated deep neural network, but how to deploy that in a tiny edge device. So that is what is important. So now, given a quick idea, what is a tiny ML? Tiny ML means the energy cost of an inference is less than 1 milliwatt. So basically, none of the available models, which are even Gen AI, I am just not talking about Gen AI, even some CNNs and ResNets, they cannot provide this kind of small energy cost when purpose of inference. So what we have to do basically? So we have to find a way to make that model optimized, and we have to know that why these models may not be required to be in this bigger size. If there is a way to make this model smaller size, given similar kind of accuracy or other factors not penalized. So researchers are working over that. So mostly there are 4 techniques which have been used, something called model pruning, quantization, network compression, and knowledge distillation. I feel whoever is used the LLMs, so they might have encountered this quantized model. In Llama and in Mistral, they have quantized model, 8-bit model and all are available. So this is basically mainstream now, this quantization, because it is the most useful part, and it is the easiest tool to use to make a model compress or make a model optimize. So first of all, what is quantization? I think everybody knows this, but just for a recap, so what is done is that network weights are over precision. So if you have a 32-bit precision weight in a DLN model, each weight is 32-bit of precision, that is basically overkilling. So that much precision is not required. The way network flow happens, the way network dynamics are there, they are not sensitive this kind of precisioning. Even less precision is quite welcome. It is most of the cases that network weights are not properly precisioned. So what can be done? So there are two ways we can do. One is called quantization aware training. So what happens is that the moment we quantize, the moment we do this kind of precision changing, say from 32-bit to 8-bit or 16-bit, there exists some quantization noise, a quantization error. Now that may trigger some kind of penalty in the overall training process, training law. So you have to accommodate that. So what happens in quantization training? So there exists a loss at every iteration of the training process. Now we put this quantization error also as another loss, and both together are minimized. So the network learning loss as well as the quantization error, if you just use both together in computation our training, it happens that we minimize both together. So what is the issue here? Issue here is that we cannot do this quantization our training if we are not able to train the model. So let's say in a LLM scenario, so if you just consider, if you just take the open source LLMs, let's say maybe Mistral or some other BioMistral or some other models, but we cannot do this quantization of training. But where we can do quantization of training, we can do quantization of training. Let's say if you want to have some discriminative models, let's say ResNet 50. So use some ResNet 50 for some classification of task. So that is quite possible because that model is also small, and maybe if you use CIFAR kind of data, that training is also quite reasonable. We can use that. So in that case, we can basically use quantization aware training. Now coming back, this post-training quantization. So post-training quantization is basically where we need not have to retrain the model. So model is already available, and then what we have to do, basically what we can do, we just directly quantize all the weights, say from 32 bits to say 16 bits. So model size in a sense will be half. Simple tricks, but we are not aware of the accuracy loss it will be incurring due to this quantization, post training quantization. Another is dynamic range quantization. So this is very much important. So this happens in an LLM scenario. This is done very often. So a clipping function or clipping action has been taken, so that the dynamic range of the weight may be very high. So we do not need that, because ultimately that do not perform that sensitive way towards the learning process or towards the inference process. So you can keep that. So if you do that dynamic range quantization, that is very much useful where the number of weights are very high. And then something integer quantization, it's same. So instead of float 16, we can have a quantized 8-bit. Now, in many scenarios, in almost all scenarios, it is empirically shown that quantized to 8-bit is as good as a 32-bit float. So even you can see there are Llama and all models are there, 8-bit models are there, and the claim is that it is almost similar kind of perplexity, all kind of accuracy are similar to 32-bit in most of the question answer and other prompting scenarios. But the point here is that in between the two, if you are very sensitive to the loss of a inference process, you should always have a quantization or training. In most of the cases, quantization training will give you a better accuracy, but at the cost of retraining the whole model. So coming back to second approach, that is called knowledge distillation. So what happens is that, what was the assumption in the first tool, the quantization, is that network parameters are over precision. Now here it is the assumption here is that network is overly complex. I will say over parameterized is part of the complexity. Maybe there are a number of layers or more and all. So ultimately network is overly complex. If we are kind of satisfied with that assumption, then knowledge distillation can be a very good useful method to make another optimized model. So what happens here is that there is a teacher model, which is a the bigger model, better model, which does the job very well. Then we can find a student model which tries to mimic the teacher model. So there are many ways we can do. One of the way is that something called distillation to minimize the distillation loss. So we have a legits there. So just compare that, and we want to minimize that. So whatever been trained in the teacher model, the way student model is trained, the same data. So it was in a sense that training process may be different, but with this distillation loss minimization, the objective is fulfilled in a similar fashion. So that why they are called knowledge is transferred. So but the main challenge here is that how to find a student model, because it can be anything. So we don't know a student model. If you are a bit kind of a domain way and other way, you know that this kind of student model may be useful or maybe quite possible, then you can use that. But the main crux is that finding a student model. If you know a student model will work, a small model will work, then this KD is the best approach to have. So the third approach is the pruning method. So I will spend most of my time here, because this is where the game changes. Until now, what happens, quantization is quite trivial or obvious. In a knowledge distillation, the student method finding is a difficult problem or difficult way of solving, because we don't know the student model at all. If you know the student model, so there are stories like that. If you know the student model beforehand, this kind of model is working for that kind of data in a ambiguous situation, we don't need a teacher model first. So we can train with a student model. So there are different debates are there, but still knowledge distance is a good process. But the game changes when pruning comes into picture. So what is the assumption in pruning method? Pruning method assume that the deep neural network is over parameterized. That is the most reasonable or most practical assumption, because it is always so. Because the deep learning theory itself asked us to make the model as big as possible so that it can learn well, learn as much as possible. This as much as possible learning basically resulted in over parameterization of the network. So what it does, network pruning, it involves removing connections between neurons or interneurons itself, channels or filters from a trained network. So how it is done? So basically we make the weights, the corresponding weights which are not important, which are not sensitive to the model's performance. So they are made zero, so that their contribution to the model's performance or model's inference is not present. So that's why they are zeroed, their values are zeroed, and basically you can say they are removed. So this is the way. So what we do basically, we find a neural network which is available, say mother network or the original network. So let's say we have a ResNet 50. Then there is a way of evaluate importance of each of the neurons, or say each of the weights, that way it's similar, and then remove the least important neuron or least important neurons or least important weights. Then the new network is formed. You can see after pruning the network structure changes because some edges may be gone, some neurons, some may be gone. So structure change, we need to fine tune or we need to retrain the pruned DNN model, and then we check the performance. If the performance is quite reasonable, quite penalty is less, then we can continue this operation as long as some constraint is met or the performance drops beyond some certain threshold. This is a simple process. Now there are different types of pruning. Something called local pruning. So what is local pruning is that, consider a deep neural network consists of n number of layers. So local pruning is that where we remove the least important weights, a fixed percentage of each from each of the layers. Let's say we want for each of the iterations or in a one shot or each of the iteration, we want to remove say 5%. So basically every time network is shrinking by 5% and 5% weights are removed. So what local pruning does, so for each layer, the least weighted values of the weights, 5% are removed. So it is kind of an equal distribution in each of the layers. So that is a local pruning. And global pruning is that it doesn't care about the distribution. If you say there is a set of weights and the least among all complete set, the least 5% of the weight are removed. So that is global pruning. So I'll come back some comparison, but in a sense the main idea is that local pruning is a kind of pruning where we want to keep the symmetry or the structure of the deep neural network a bit similar. If you know that structure similarity is an important issue, then we'll always go for local pruning. but where the performance or the amount of pruning is more important. So if a local pruning, if you go up to say 20% of pruning, given say 1% of accuracy drop, in global pruning in the same network, it is possible to go as long as up to 50% or 70% of the pruning, given similar kind of say accuracy drop. Because in local pruning, we are constrained for that each of the layers should have similar kind of, similar number, similar percentage of weight to be removed. So this you have to make the distribution uniform. So that is not that constraint is not there. So either unconstrained environment, so global pruning always performs better, but it distorts the network structure severely. So in a sense, another is called structured pruning. So where we want to remove a structure entirely from the networks. Let's say instead of knowing each of the weights which are not useful, so we can know which of the layers are not useful entirely. So then this layer or a channel, say is a 3-channel network, so maybe one channel is not at all working to the model's prediction, so we can remove that channel. Even some layer which are not sensitive to the network learning, so we can completely remove that layer. So that is the structured pruning. And unstructured pruning is where this relationship, because all weights in a DAC kind of scenario, there exists a relationship. So this relationship are not kind of maintained, then we call it unstructured pruning. Here again the similar thing, the unstructured pruning always, or I not say always, in high probable cases, it performs better than structured pruning. So I told you how network is pruned and all, but what is the way of understanding which weights are to be pruned? So there are different ways. So one of them is called magnitude based pruning. So if you see that example, say this is a filter weight. So these are the 4 elements of the. So if you use L1 norm, and then this way, this importance for each of the weight, we got the importance score, and then if you want to say 50% pruning, then we see how this pruned weights ultimately had been there in the network. So this way, this 3 and first there are 3 and 0, 0 and -5. So this has to be noted. Now if you use L2 norm, so what it's done, so it in a row wise, if you just want row wise, then we see that first row and second row, if you compare, so first row magnitude is much less than or less than that of the second row. So we just eliminate the first row weights. So this is the how the pruned weight been used. Now you can always see, if we use one of them, let's say when you use in the same network, when you use L1 norm, kind of say element wise and importance scoring, the pruned weight, and if you use L2 norm, the same way the importance scores are different, and the pruned weights also look different. So what should we do? So basically we cannot do anything. It is mostly trial and error, but there are some chances when you want to have a more regularization to your network, that regularization effect come into the network. In that case, it is been there are evidences that L1 norm works better than L2 norm. So this is something called the world of pruning. So first we have to know what to prune. So do we prune through a local, structured, unstructured, global way? So this you have to, a priori you have to understand. And I have just given an example of magnitude-based pruning. So there are gradient-based pruning, there are land-weight pruning, there are information-centric pruning also. It's possible, but mostly magnitude-based pruning are used because other than that, the network dynamics changes much, higher than magnitude-based pruning. Now, another is when to prune. It can be, we can prune the network, before training also. There are ways we can do. After training also there can be, and during training. But most of the time we do it during training because we come to know the complete loss at the very consistent way, and we a priori know that this is the loss expected. And another is one shot or iterative. So if you go this is an iterative pruning. So we do the pruning once and then go back and then go. Say you want to prune say 5% each time and you want to achieve say 50%. So you have to prune some maybe 9 or 10 times based on that, because it will be a way we every time 5% will be pruned. So that way we compute and number of pruning steps we can find out. And another is, say we can even in the first step itself we can go one shot way, means say 50%. Every first time itself we go for 50% pruning, so we don't go any iteration. That is also possible, because the crux here is that training cost, because every time we do this iteration there exists retraining. There are data sets and models which are very much costly when training comes into picture. So where we don't have that option to retraining many times, so we have to do one shot pruning. So coming back, so there are many ways. So world of pruning is basically overwhelming. So if somebody wants to optimize their network and they understand pruning, what to do, and they thought of, okay, my network is over parameterized, let's do pruning. But now given that so much options available in this pruning world, they may be confused, they may not understand what should we do right now, because all possibilities exist even together. Even in when to prune also, before training, during training, after training, you can do. Basically all the possibilities are existing. So here comes something called lottery ticket hypothesis. So this is one of the groundbreaking hypothesis put by from MIT. It came in 2019 ICLR. So surprisingly, it is one of the most simplest hypothesis I have ever encountered. So what it says is that a randomly initialized dense neural network contains a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. It is a bit, so the way it is written, it needs some explanations. I will do it, that explanations will be done. So again, there comes a assumption. So pruning, what is the assumption? Pruning, in a sense, the assumption is that network is over parameterized. That is a simple and generic assumption. When coming to this lottery ticket hypothesis, the assumption is that network is over parameterized, fine, but a network and it exists with its equivalent subnetwork. So that is important. That assumption is a strong assumption, and with that assumption, this lottery ticket hypothesis is presented, and it is quite successful in real life scenarios. So you can understand the difference. So it is a much more strong assumption than the pruning assumption. So I'll go here. Okay. So what is the motivation here. So a randomly initialized weights and train. So we have a model, so which has been randomly initialized, then the weights have been trained weights exist, and let's say its test accuracy is 90%. Now we prune the network, and there exists some over parameterization. We can remove those, and there is a chance we can get similar accuracy. There may be possibility, and there always exists a possibility if we say the network is over parameterized. Now, if we randomly initialize weights and train, if we do this process here, same network, the net accuracy drops, so 60%. So there is some kind of mismatch is going on, and that is being exploited in rotating hypothesis. I am pausing a bit, just pausing to give you understanding what is happening. Let it, this animation runs for a few seconds, maybe say 30 seconds. Then I will explain one by one what is happening here. Just look at this, try to understand as much as possible. Okay, so what's happening? So there exists a network which is initialized by say W0. Okay, now it has been trained, first trained. So this is the train, first iteration. So it has been trained, and then we find with say magnitude pruning, this M. Okay, come back. Yeah, M1. So what is that? That is a mask. So that is the first pruning networks or pruning weights that has to be masked. So that is the say a binary mask. So that is the element wise multiplication. So first method, say we want to, in each iterations we want to find out 5% weights. That means which are least magnitude 5% of the weight, and that set is the mask who is at least 5%. That becomes 0. So if you make a element wise multiplication, so this is where our this first pruning happens. So that is quite natural. So that way the pruning happens. Now the main small trick what they have done is that, yes, this winning ticket. So what is that? Where is the difference? Difference is that now at the time of retraining, it has been reinitialized with the same random weights which has been there at the beginning. So it is quite contrary to what we feel. So it has been trained with the first set of pruning. We just find out the weights which are to be retained, and in the second run when we retrain it, that is these weights are now randomized, same number or same random number, same random weights they have been assigned to. Then again it is retrained. Now that way, say n number of times this same cycle goes, either there exists a stopping condition or there exists a performance condition. Say if you want to iterate for say 5 times, that's okay. Or you want to say that loss is coming say 1% or 2%, that's okay. But in a classical lottery ticket hypothesis, we say that there exists no loss. So we'll basically stop where there is a loss, and before that, say in nth step we find there is a accuracy penalty, then n-1 step that network is chosen. So see, this is a very simple step. Only thing they have changed the initialization weights to a random weights, which has been done at the initial step. Small change they have done, and the one at each iteration which the weights exist with this random state, they call it winning ticket. That means it is basically the initialization winning ticket. The ticket of the network, the subnetwork with the same initialization factor exist after pruning. That is called the winning ticket for each of the iteration. So it is the very simplistic way, but the main thing is that it works wonder. So what we have done, so we have taken this up very naive way. So we have used this and we have put our small novelty there, and we use this for some applications. So I'll come back to that, but before that, just what is the application? Application is now this pruned model exists. That means we have a network which is less parameterized, and there is a chance we can deploy the network into real system. So we'll come back what we have done with that. So how real system has been developed using LTH based network pruning. Last but not the least, the approach is called network architecture search, or somebody a bit in a old fashioned way, you call it neural architecture search. So if you have a neural architecture or any network architecture, say in a generalized way, so basically it is a searching over a set of possible network or neural architecture. So what is the assumption? This is the only approach where there exists no assumption. Basically, we are growing a network which is, in a sense, doesn't have any prior knowledge, but we know that in a systematic way, if we can properly do the searching process and some kind of exploitation and explorations, that kind of in a RL domain, if you can consider and if you can deploy that, they are possible, we can get a near optimal result, a near optimal model architecture. So there are a number of ways it can be done. So one of them is proxy task. So because this, neural architecture search or network search is a very expensive process, because you have to go on searching and there are n possibilities and n maybe millions. So we have to know the subdomain of it, and then the task may be very much complex. We have to find a proxy task of it, and then that way we have to know a learner. Learner goes on like that architectures, and then based on the proxy task response, it updates. So there is also proxyless approaches of that, but it is a quite involved process. But problem here is that we need a big infrastructure to kind of find out a model which is through neural architecture search or NAS. Okay. Just hold on. Okay. Giving you another idea, that robustness and model size reduction. Why robustness come into picture? Basically, if you find a deep neural network and its subnetwork which are equivalent in performance, then where is the cost? is the redundancy in the deep neural network are of no use? All the theories, all the evidences of a deep neural network are of little use because there always exists a subnetwork, or the exist is always over parameterized. This may not be the case always. Redundancy in everywhere serves some purposes. If you see our human body, if you see everywhere in any critical systems and all, there exists redundancy. Redundancy is where that force the system to be robust. Otherwise, if redundancy is not there, a small failure in one of the nodes or one of the subsystem, subcomponent will be catastrophic and the entire system will fail. This is not the case in any of the real life models, be it mechanical, electromechanical, electronics, and computation. And that is where also deep learning or deep neural network trumps because of the redundancies. So now the moment we remove the redundancies using this kind of techniques, the cost is most likely in the robustness. It may work very well in the known domains. The moment we want to take it in out of domain or out of distribution task, out of distribution data, there is a chance or high chance that reduced model will fail, where the main model or the over parameterized model may not fail and it may adjust itself because it has been, there are weights which were not useful in a particular case that becomes useful in some out of distribution case. That's why these models become so large. So what is the definition of the robustness is quite simple, that it is the resistance to failure when input is part of within a well-defined perturbation set. So in model size reduction or optimization, so there are basically three scopes. So we are given a robust model. So robust object detection model, maybe YOLO and all, which are quite robust. But how to reduce that robust model, given not only its constraints are satisfied in terms of size, parameters, and accuracy, also its robustness has to be preserved. So that is the first task, easiest of them. Second task is, we are given a model, but there is no robustness quantified. So then we have to measure the robustness or quantify that, and then step one or number one is followed. Then you have to find a model, small model, which is not only in a better parameterized, but also in a way it is classification or test accuracy is same and robustness is also same. But the real challenge is post-training robustness. As a constraint, should we go for with accuracy constant? Do they work together? Basically, we don't know. This third question is a bit difficult to answer, because whenever we change a scenario in a test accuracy perspective, because all these lottery ticket hypotheses, they have been proven over some given test accuracy, but in a large set of unknown data sets, how they react, it is not known. So in a post-training robustness in pruning cases, it is not known. And also how to quantify robustness. Till that there are many definitions, but it is not as focused or as as kind of say quantified as accuracy, sensitivity, F1 score like that. So even in literature there are debates on how to quantify robustness. So that is also a problem. No, this is quite given. So robustness measure is also quite understandable. So this is that minimal distance adversarial example that will not part of the system. So or that way it will part of the system. This what is that particular sweet spot due to which network changes its decision. So this is the most simple way. If you also consider that, that is quite fine in many of the scenarios. So I just discussed this paper. So this is called drawing robust scratch tickets. Subnetworks with inborn robustness are found within randomly initialized networks. So this has been published in UDIPS 2021. So what they have done basically, so they pose the question, can we find robust subnetworks within randomly initialized networks without any training? What is this? Say here, this winning ticket. So winning ticket is it has been found out. Now for robustness quantification, robustness identification, do we need another set of training over that winning ticket? So there are literature, they say it's required to have another set of training on the winning ticket to make it robust or to find it is robust or not. So they claimed basically this is a first paper that way it came out. They claimed that LTH can be extended, lottery hypothesis can be extended for robustness, and we can find a robust lottery ticket hypothesis, and that will practically lead to efficient subnetworks. And this efficiency means the network, even if without retraining for robustness, it will be robust. So, but the way they have done that is also quite intuitive. So what they say is that this winning ticket, they call it simple the robust scratch tickets. So what is that? So what they have done, so a sparse and learnable mask M associated with the weights of randomly initialized, that we know. So update those M's without changing, only update M without changing the weights. So this is the equation it will follow. So it is what is this? Basically, there is a perturbation, small perturbation applied to the input, and the weights which are basically providing that adversarial outcome. So that basically given a wrong or that changes the loss, and there is a affecting to the loss, that are masked, that small set of the mask, and this process is used as a minimax problem. Now given that is a constant search, so we cannot use gradient descent, so we have to do PGD, projected gradient descent. So in a sense they have not done anything different. So instead of a traditional loss function where we don't have kind of small perturbation, they have used as perturbation at that means learning method, and the weights which are sensitive to that perturbation, they are only masking those weights. So that way it becomes a bit efficient, and also they are not changing the network dynamics in a larger sense. So that's why it is not only a good in a robustness perspective, it is also efficient. So we have also published one paper in 2022, but this is a mostly on a implanted device, and we have shown that this rotated hypothesis, if we use for this disease detection using ECG, electrocardiogram, and we can basically implement this to a small device, and that can be used for different purposes, or say disease detection. So I just give you the result. So novelty wise, what was that? So what we have done, we have taken the condition of a single lead ECG. So if you go to a hospital or some diagnosis center, the ECG what you have been used, that is called 12 lead or 6 lead. So you can see it is been there are different leads are there, but there exists single lead ECG what you can purchase off the shelf, and even many of the smart watches, it is part of it. Now then you can directly at your home, you can directly capture that ECG markers. And one of the biggest threat in cardiac disease, it is not only heart attack or stroke, something called atrial fibrillation. Some of you may know. Basically, if it's getting undetected, it leads to stroke. So if we have a timely detection of atrial fibrillation, in US there is a study, so it is more than 65% of stroke incidents can be minimized. So our attempt was to deploy a model into your sensing device or your smartphone or your smartwatch, so that you can round the clock, you can monitor your heart health, and who are the vulnerable ones, who is having almost already a cardiac disease, which is having high BP or high blood sugar. They can maybe in a day they can just check this, so it will take 1 minute of time. So this is the figure, so we can see what is the data. So we have used some publicly available data. So this is in MIT PhysioNet, you can know, somebody may know. So MIT PhysioNet challenge happens every year. So this is MIT PhysioNet 2017 challenge data set. And by the way, that challenge also from TCS Research, we have participated, we have owned that challenge. So there are MIT and other US universities were there, Philips Research were there, but that time we won the challenge. So detect this atrial fibrillation condition. So this is the network. So the challenge in 2017, that same thing we have used, but we have used ensemble machine learning network. But what happens to that, this ensemble machine learning can be used, but the tuning and other operation cannot be performed. So instead we have considered this one model, which is also equivalent. This is published in 2019. They have not participated in the challenge. This is from Stanford and this is from Androin's group. This is the most pioneering work is that. So but they couldn't beat us. So if you go through that paper, so they have cited our paper also, our work, but their results in same data sets are at par or less than ours. So they acknowledge that they couldn't beat us anyhow. But the main thing is that they have considered the deep neural network, kind of a residual network with residual connections, and that is useful because the moment we get a deep neural network, so we can use this kind of LTH techniques to reduce that. So this is a deep neural network. So if you want to deploy it, it is around 110 MB in size. So in a smartwatch or in a sensing device, even in a mobile phone, it is a bit overwhelming to deploy for a particular task. So it is also not advisable, and it may not be deployed in many smartwatches and sensing devices. But we want to use that for in a portable device, handy devices, not in laptops and all, that will be of no use. So this is what our result is. So you see that with benchmark we are almost similar, a bit better. Benchmark means that Andrew Ng's model. So this is LTH ECG. So this is not the same model what I talked about, our ensemble model. So what we have used this deep learning model. Then we have done some lottery ticket hypothesis and put some constraint over that. So that is very small constraint. What we have done, so we know what are the target hardware condition. Basically, all this mapping function and this masking are been every time the number of mask and the distribution of the mask. So that is been governed by the target hardware. So target hardware footprint is there. So based on that, intelligently, every time this masking amount, or say every time this will be marks this, and there is some kind of to and fro movement with masking, non-masking, so that it goes to an optimal performance to the given constant. Let's say we want to say reduce the model size, say by 100 times. So now we find out how many iterations is possible, and also if you say it can be done in 10 iterations, it can be done in 20 iterations. So how it is been done with some conditioning that has been there in the paper. So ultimately what we have done, based on that condition, we want to target the network parameters such that the test accuracy doesn't fall, or even if it falls very minimally. So this is our result in comparison with the benchmark DL model. Now, if we use different pruning techniques, so there exists, I told you, that global pruning technique, that layer-wise pruning technique. Also in global pruning technique, you can do further fine-tuning, and also layer-wise, you can do further fine-tuning. Now, if you go basically within some drop of say 1% and 2%, say mean F1 score, so the parameter reduction factor in global pruning is around 2.5. Means if we say 100 MB in the model, with global pruning you can get a parameter reduction factor 2.5, means your model size is reduced to say 40 MB, close to that. So layer wise also 1.9 times, that global plus fine tuning is good. So 48 times, layer wise 11 times. Now with LTH and our method, we achieved 142 times model size reduction given similar mean test F1 score. That is where it makes some sense. Now we have a model which is sub MB in size, and now we are ready to deploy that model to sensing devices, because we have in fact done that. So that sensing device is available and model is already been deployed. So this is how it works. So we can see the stability of our work, so that the method we propose that LTH ECG. So even if you reduce the parameter at each iterations, so it is stabilizing, it doesn't fall that drastically. So it falls after this 172, and this next iteration it will be 100 and 210 kind of. Anyhow, so then that is false. So but each time it very closely following the test mean score. But in other methods, you can see that after some time it drastically falls. Okay, so that much I feel sufficient for the time being. So something a bit lighter note. So what we want to do now? So human being 2000 years ago, so we are thinking of how to grow food, where to grow food, how to communicate, how to predict weather, how to travel long distances, how to navigate oceans. So that's why some invention came, be fire, be the wheels, be the ships. And medieval age, same. How do I grow food or hunt? How do I predict weather? So they found some ways. So ancient time there are no ways, but after learning the environment, learning our capabilities, we come up with some tools, the same set of problems. Then came the Industrial Revolution, same set of problems. Now we work in a different way. So we communicate differently, we grow food differently, we predict weather differently, we travel differently. So now AI revolution. So what is going to change? Till now, these things are still same. What was there in the Industrial Revolution, what is now in AI revolution, but it is changing at the background. All these discussions what we are having, maybe one day it will make some sense here, and the way we do these stuffs may change. So we don't know. I don't know how it will change. Maybe instead of human beings in the loop, maybe some bot will be in the loop. The way it change, that is my perception. Yeah, that's it from my side. Thanks.
Thank you, Dr. Arijit. So it's very nice. I mean, very informative talk. I mean, not only that, it was, I mean, it's kind of a curiosity that I was looking for. So that's nice about the pruning techniques. So based on that, one question I'll ask that. Suppose one model is, I mean, we're working on. So that we understand that required actually a lot of parameters. So how to identify that this is possible to reduce the parameters and pruning is required?
Okay. First of all, pruning requirement comes from the target hardware basically. So if your target hardware doesn't require pruning, requires small models, so why should we have a cost of doing the pruning? There always exists a cost of pruning. Now I will tell a different story. This lottery ticket hypothesis, if you go through that paper, very easy to read paper, at least the first paper. So they have not used lottery ticket hypothesis for pruning, but they have used lottery ticket hypothesis for network regularization.
Okay.
So what is happening, if you have that many means kind of weights and all, we need some regularizer. So that L1, L2, all these things come into picture. Lottery ticket hypothesis is one of the best regularizer if you go through the paper and if you work that. But what it does in the sense, it is not only reduce the network weight value, but it's basically eliminates the network weights. So in a sense, if you that thing, so that's why we have used that not for a regularization, but for pruning purpose. Coming back to your questions, it all depends on the target hardware, and if you want some pruning, then you always think that there exists a target network which may have some constraint, real-time constraint, size constraint, and other energy constraint for the inference. Or if you want inference, even if you don't have a constraint or some kind of regularization in the way that inference may be better, and out of distribution also it is possible with this regularization, then you can always use at least the LTH one.
And the classical regulation and LTH, is there any similarity or something different? What how it
No,
is different?
classical regulation, it keeps the weight. So if you use L1 regulation, what it does basically, it basically few of the way I show very briefly. So if you just in the loss function, you just add that L1 norm basically for each of the weight. So what it does, it wants to minimize that every time. But in a effect, that changes the network parameters, but not the network parameter dynamics, but the network parameter weights. But here the network parameter dynamics is changed. So there are few parameters which doesn't exist in rotating hypothesis. So there is a drastic change. It says that in a L1 or other regularization, same network exists. Means the parent network and the regularized network is same, only the some weights change. But here the network is completely changed, you get a subnetwork.
Now, one more point that can you compare your work that with the after the pruning. So one is F1 score, I clearly understood. So 142 times, how do you how is that computed? I didn't understand when that 142 times.
140 times is the number of parameters reduced.
Okay.
So 142 times means the one. So if you have a say I'm giving a very simple example. Say 142 number of parameters exist in the parent network and our pruned network, then only one parameter exists.
Okay, fine. Yeah. So next, the participants would like to ask some questions to the speaker, then please kindly come up with your questions.
Hello, sir. First of all, I want to congratulate on winning the PhysioNet challenge and on the successful deployment of the model. And now that we are speaking about pruning, what major factors we should be taking into consideration, say, if we say that the data pruned set has not been taken into consideration, and we have the data set as such, the raw data set we are taking into, if pruning doesn't take place, so what happens and what factors should we keep in mind if we are not pruning that, and what would be the major limitations if we are doing that?
So do you mean the model pruning or data set?
Data set. I'm talking about the data set, sir. We are talking about prune. We are taking into consideration the pruned data set.
So here the idea is not pruning the data set. So data set is fixed. So data set means, if you mean the training data set, it's fixed. We are talking about the model. Here the model weights are pruned. So data sets are fixed. So data sets are used for training, or if you have a validation data that are fixed.
Yes.
We are not pruning at all. So that doesn't matter, or that doesn't make much sense, because ultimately you have to deploy the model.
So okay, I correct my sentence. So if we are not taking into consideration the model pruning,
okay.
So what would be the major limitations of that particular, what would be the most considerable challenges we would face if model training, pruning doesn't happen? Or what would be the major factors we should consider?
So if you cannot do model pruning, then what I understood that means, if you cannot do model pruning, so model quantization can be there. So there are some cost associated with model pruning. If you cannot do something to incur that cost, so that quantization is the most effective way. Okay. And other than that, basically it all depends on your target. So your target hardware is so much constrained. Yes. So quantization may not be useful. So in a sense, so there are binary nets are there, but that is a debatable part from Google. But where they have only one bit for each weight, but it doesn't work. So in a sense, if you see the today's perspective, mostly 8-bit network weights are common. Now, given the most of the network weights in a classical sense are 32 bits, so in a 8-bit sense, you are basically reducing 4 times. So in a sense, it has been limited to quantization by 4x. Okay. But our case, if you say in a different way, you want to deploy a model for a sensor device. So in a card sensor, in your smart watch you want to deploy for some task. So there this 4x will not work because the existing model may be 100 MB, 500 MB in size. We need something which is a 100x kind of reduction. So then the model pruning is the most effective approach.
Okay. Thank you, sir. Thank you so much.
Any other participants, please can raise.
Sir, I have a question. So,
Yeah, please.
yes, sir. So we have different quantization methods. How do we know that the model is actually having the that is the trade-off between the computational efficiency and the model performance? How do I determine that uh, which quantization technique is most suitable like that for the particular thing, and also the accuracy loss introduced by quantization by minimized while applying the maintained efficiency?
Okay. Yeah. See, it all depends. It all depends on the cost you can incur. Means computational cost. Means if you can retrain the model, the quantization error training means at the time of training, you put the quantization error to minimize as well as the loss. Then that is the best thing can happen, because then it will find out those quantization weights that are also optimal. But the cost is very high because you have to retrain the model with quantization error. Now, if you have a bigger model which we cannot retrain, so there the limitation of the quantization is very, very high. Means we have only, say, from 30, if it is a 32-bit precision weights, we can only go to 8-bit and check that how much accuracy loss it is happening. Or you can have a dynamic range clipping. Dynamic range clipping means, say it is a 32-bit, you clip the dynamic range, then you make the quantization. So how will have a accuracy drop, limited? So because quantization doesn't do anything to the learning method. If you do the post training quantization, it only changes the network weight precision. So then it is basically a matter of chance. If the network weights which are important in a over parameterized network, which are important, if they are over precision, then quantization will give a very good result. Even if you see the today's Llama 3, that 8 billion, or Llama 2, this 1 billion, 3 billion, which are 8-bit models, they are very much close to the 32-bit model, because there are so many weights that this precision doesn't matter, because the MAC operations are so huge that if there is a precision loss somewhere, that is been nullified in some other way. So it is a law of large numbers take place. But if your network size is small, if your number of network parameters are small, then it is always a matter of chance in post training quantization.
Yes, sir. Thank you, sir.
Sir,
Hello,
I have a
sir.
question. I have a question, sir. So this is regarding the pruned model. I mean, the pruned model, the efficient pruned model is available as a localized model, or it will be again available in the network?
The pruned model is available for you to deploy. So basically it's similar. So same basically you have a model M. After pruning you got M prime. So that is available to deploy directly.
Okay. Again, can it be imported? Exported to the base existing model?
No, this is not a reversible process.
Okay. Thank you, sir.
Even none of the compression, if you say quantization, pruning, these are not at all reversible.
Okay.
Basically you don't need. Basically you have a idea is you have a bigger model, you want to make a smaller model. So this bigger model will always exist.
Again, the pruned model with the efficiency and can be made as a base model. Can be overwritten to the existing model, right? Just
yeah,
thought.
that's why if it is as good as the base model in its classification or some performance criteria, so it it is basically replaced by the base model. That's what we have done in many cases. We have deployed it. We have not deployed the base model. Base model is in the lab, but when we deployed the pruned model, which is as good as the base model.
Okay, thank you, sir.
Good evening, sir. Sir, can you please tell the specific challenges during pruning process of federated learning?
Yeah, I've not done anything on the federated learning, but see, the problem is if you have a distribution or distributed learning, say pruning or lottery ticket hypothesis, if you see, or if you want random scratch tickets, so the assumption here is that centralized learning. So if you have these things in a distributed fashion, so this subnetwork in a centralized subnetwork on a LTH and a distributed subnetwork, there cannot be same network which is distributed in a federal learning and same network which is centralized. If you do a individual LTH, they're highly likely that the resultant networks will not be same. So this kind of techniques may not work apart from this quantization.
Okay, sir. Thank you, sir.
Good evening, Dr. Arijit. I just have one quick question. So pardon me because I have a theoretical computer science background, so I'm pretty new to AI and ML, so pardon my use of words if they are not technically correct. But the question is, we were trying to deploy a pre-trained YOLO model on an FPGA board, which in turn would be mounted on a drone. So would it serve the same purpose, like the model compression, would it serve the same purpose? Because from the discussion that you had, I find that you've been focusing a lot on the edge devices. This is kind of a different scenario. So if the compressed model behaves the same way as the base model, say by testing on the same test data or otherwise, would it work the same way, or do I need to look at something else? Because this is something we have been wondering about. So the YOLO V9, V8, they are pretty heavy models, which we are not sure if we can in fact configure on an FPGA board at all. So we were looking at whether there are model compression techniques available which we can use in order to put it on an FPGA board. So does it make sense, or we look at our strategy or whatever?
So you have to do it in a different way. So you just go to the literature. I feel in this year or last year, most probably this year, something called edge yellow. Just find out. Most probably
edge yellow.
Yeah.
Edge yellow. Okay.
Yeah. You just search. So that is where they have come up with a network which is as good as a YOLO, and they have used all kind of model compression techniques what have been discussed here, and they have come up with this edge yellow. I think that will serve your purpose. If that doesn't serve your purpose, then I will basically say that you use edge yellow as your base, then you further reduce it by these kind of methods. So don't go directly YOLO V9, V7 or whatever. So that will not serve your purpose. Go for edge yellow first.
Okay, yeah, that's really helpful, sir. And one more thing regarding the robustness measures, right? So apart from testing on the same data set, are there any other robustness metrics that we can test and see? Are there anything, would you be able to give any pointers on how we can ensure the robustness with it? Because drone is where we have this real-time decision making to happen so that it can take a real-time decision during navigation. So is there anything that can ensure the robustness with respect to the challenges involved in model compression? Are there any pointers where you can give me, like measuring the robustness?
See, the robustness as a whole, it is not defined in a quantitative sense in a distinct way. It is not kind of the definition of accuracy or sensitivity. There are differences in opinion, but the basic structure is that under some adversarial condition, you have to test your model. So you just do few of the things, very quick things you can do. Some adversarial regularization library are there in Python. So you just study your model. If they are having similar kind of response under adversarial condition, just simply plug in that library. So it will quickly provide you the result. If that is not possible, then we have to basically introduce this kind of robustness in the learning itself, because the model can learn something out of distribution if you make the model at the beginning itself learn something which is not present in the network by some kind of small perturbation. But before that, you check with your adversarial regularizer, and given the similar set of test data, say that how it works. If it works quite satisfactory, you don't need to do all these stuffs.
Okay, got it. Thank you very much. Thanks a lot for the pointers. We'll try to work on these lines. Thank you very much again, sir.
So few questions are also on chat box. So one question I can say that is the LTH always ensure a subnet model?
So that's why. So LTH is lottery ticket hypothesis. So there are controversies. It is not proved. So there is no proof there. So they have shown empirical evidence that most of the DNNs have subnetwork which is as good as the main network. So that has been empirically established. Even what our work is there, we have empirically established that it is 140 times reduction is possible. But you cannot claim that in any model, this 142 or any x times which is greater than 1 is possible, because there is no proof. So it is all empirical. So, but most likely in a today's world, these deep neural networks are always over parameters, because we don't know, and we want to put this robustness, we want to put more kind of data set or training as far as possible. So that kind of notions are there. Given that notions are there, so you always tend to over parameterize the model. In that sense, there will exist a subnetwork, but there may be a chance, because it is not theoretically proven.
And as the model cost is high, so any way to train the model on low configuration system?
Yeah, so one thing what we have done also, we have fine-tuned the model. Means every time we do not need to retrain the model, something called differential training, what we are working on. So every time it's a very small thing you can do. Wherever there is a change in the model dynamics in every time, if you take a kind of a note or map of it, in the retraining part, we only use those data sets. So the retraining cost become less. So for the first time, if you have a data of say 100 MB, then maybe next you can have a 50 MB, maybe next 30 MB if you have a differential training. But that literature is growing, but you have to be a bit careful there, because differential training always takes into account kind of a greedy way. That may not be always optimal, but it may work. So you can try that.
So participants, if you have any other questions, you can please reach to us, and also if you would like to interact with the speaker, then we will try to make you reach to the speaker. Once again, thank you, Dr. Arijit, for sharing the nice ideas and the knowledge that the participants will be benefited. So with that, we can close the session. Again, I just want to say to participants, so we have tomorrow again session starts from 6 p.m. So we have again two sessions there tomorrow, and so 2 more declarations for the participants only. So many people have asked about the attendance. So we are automatically tracking the recording. So where you can the participants with Google Meet only particularly. All are requested to attend the sessions from starting to end. No separate Google form link will be shared for collecting attendance of the session. So all the in and out will be recorded there. And again, so feedback things, I'm just telling that the feedback of each session will be collected by ATAL portal. We are not going to collect it separately by Google form, etc. We are not. We can note the specific. You can note the specific feedback of the session, and later once the FDP over, you can give the feedback once it is enabled. Okay. So it is on portal itself. So we don't. We are not going to share anything in any Google form, etc. So hope all the participants understand that. So that's all. So we can
Okay.
close. Yeah.
Thank you. Thank you all.
Thank you.
Okay. Thanks. Bye.
Any other queries from the participant can also ask me. Okay, so we can close the session. Fine.